We are going to work through slides 10 through 12 today. And we have it on paper in class, and we're going to upload pictures. You can do this online by just typing, making new text boxes here, and then also graphing it. So let's see what we are looking at. So tweaking parameters. What kind of function are we dealing with whenever you look at all of these graphs right here? Exponential functions. Okay. And how do we know that they're exponential? What's something that we can just look at and see? The curve. Okay, so curved graph. And then also, let's look at the recursive rule. We have the start and then now times 5. So that multiply times 5 also tells us that it is an exponential. And then if we look at the function rule, see how we have an exponent as our x value? That also tells us that it's exponential. So all of these have the same exact graph, but we are going to change these. We are going to add another function on top of it and look and see how they're changed, how they're different. So we'll look at the first one. I'm going to change, so this one has a start of 3. So my new recursive rule, I'm going to start it at 5 this time. Then my next, so that means the next value of my function will be whatever I have now, and I'm still going to keep my rate the same, times 5.
All of them supposed to be the same?
Yes, all of them are the same because we are going to write a new one and then compare the two. Yep. So let's figure out a little table here, x, y. So we're not looking at this. It's already been graphed. We need to make a table so we can graph the new one that I just gave you. So if it's start equals 5, that means that my 0 value is 5. And that's also my y-intercept. So then the next value, say when x is 1, what operation's happening between the y values? Multiply, because it says what we have now. So we have 5 now. Then we do times 5. So times 5 right there. So then our next value that goes here that matches with 1 when x is 1, 5 times 5 is 25. Let's do number 2. We need to get our next y value. So how do we get our next y value? What are we going to do to what we have now?
25 times 5.
Yeah, 25 times 5. What do we get? Yeah, 125. Okay, let's do another one. 3. So we're at 125. To get the next one, what do we need to do? Times 5. So this is 625. So let's graph it. 0, 5. So 0, 3 is right there. So 0, 5 would just be a tiny bit above it. Then 125. So if this is 10, then this is 20. This is 30, right?
Yeah.
40, 50, 60. And then my x's are just 0, 1, and 2. So 1, 25. So 1 and up to 25. To 125. Ooh, only goes to 7D. Let's see if I can just kind of add to it. So that'd be 80, 90, 100, 110, 120, 130, something like that. Because I want to be able to see how it really looks. Only 2 points. It's hard to tell how the graph is going to look. So let's do 2, 125. Looks like that. So let's connect the dots as best as you can. So it's not straight, it is curved. So it is still exponential. So now we need to come up with the function rule. So let's look at the original graph and the original function rule. See how this is 3 times 5 to the x? That first number, it represents what? The y-intercept. Yeah, so what's the y-intercept on this one?
5.
So, yep, 5. So f of x equals 5 times 5 to the x. So the 5 is our y-intercept. And then this other 5 is our rate, what we're multiplying by. So this one had the same rate as this one, just a different start value. So write that here. Same rate, different start. With linear, if you have the same rate, how do your graphs look? Goes in order. So linear, if you have the same rate, like y equals 2x and y equals 2x plus 5, they're parallel, exactly. Because one would be like plus 5 up 2 over 2. One would just be right here. This is a rough graph, something like that. So with exponential, are the lines parallel? No. So exponential, you can't say they're parallel, but do they look like they're going like together in a way? They're going to continue to spread out. They're not going to be the same distance apart, but you can definitely tell that they're going at the same rate. But one of them, this one, is going to be stretched a little bit more because it started at a different point. So it was a stretch. Stretch was the transformation. Okay, number 2. We still have the same graph, same original recursive and function rule. So this time we are going to start at 1 and keep the same rate. So it'd be next equals now times 5. So let's do the same thing as we did earlier. Make a function. So we have, what is our 0 value? Our y-intercept? 1. Yep. That's what we start with. All right, the next term, what are we going to do to what we have now? Times 5. So that'll be 5. Number 2, when x is 2, what is y? Times 5. So 5 times 5, 25. Let's go to the third value. Times 5. 25 times 5. 125. Let's go ahead and graph it. So 0, 1 is going to be below the 3, just above the x-axis right there. And then the next one is 1, 5. And then 2 would be 25. So this is 20, 30, so 2, 25. And then the third one would be the 125. But I have 3 points, so I can go ahead and connect these. It's going to be something like that, right?
I want you to move so you can see the screen at the same time that you're writing. Can you move around? You can move right there. All right, we're just moving the chair around so you can look at the screen.
All right, now we need to write our function rule. Well, let's write, over here we put same rate, different start. What did we change on this one? Start. But what did we keep the same? Okay, so same rate. Again, different start. So how did it change the graph?
We started at 0, 1.
Yeah, we started at 0, 1. So it's like moved down. But what else about this graph? Is it stretched? Is it going faster or slower? It's going to go a little bit slower. So this is actually called compressed. It's smushed down a little bit. So think about whenever you compress something, you have a top and a bottom that push down on each other. That's called a compress. Stretch is like you take a balloon and you pull it. So we can compress it or we can stretch it. The rate is the same, but because we started it at a smaller value, it's not going to increase quite as fast. But look at the numbers, 5, 25, 125, 625. This one is 1, 5, 25, 125. Let's write the new function. F of x equals, how do we write the function?
1 plus 5.
Yeah, 1 is our y-intercept times 5 to the x value. The rate raised to the x. So anytime you have an exponential function, your x value is the exponent. So it feels like I'm saying like the same phrases over and over. Exponent, exponential, the x value. Number 3. We are going to start at 3, so we're going to keep our beginning amount the same. We're going to change our rate. So next equals now, we're going to do times 2 instead of times 5. So let's make our table of values. So we're going to start with what? What's the start value? 3. Okay. And then we are going to go to, when x is 1, what are we multiplying now, what we have now by? So times 2. So what do we have now? 6. Okay. Number 2, we're going to multiply what we have now, the 6 times 2. That gets us 12. The third one, 24. So what do you notice about the rate? Is it going faster or slower? Slower. It's increasing a lot slower. But it starts at the same value. They have a y-intercept that's the same. So your intersection point is at that 3. And now 1, 6, 2, 12. Let's say I want to do 3. 3, 24. So this is 20. This is 30. So 24. So it's not going at a straight line because this is really slow. And then it starts picking up speed. Just not near as fast as if our rate was 5. So what can we write about how we changed it? Is this a smaller or a larger rate? Yeah, so smaller rate. But then we have the same start. So was it stretched or compressed? Compressed. It was pushed down. You take this one and you compress it down, it could look like this. So this is a compressed or compression. You'll sometimes see it as stretch or compression. Let's write our new function rule. F of x equals
3 times 2 of x.
awesome. 3 times 2 raised to the x value. Getting the hang of it. Not too bad. Let's go to the next one. I'm going to keep the same start of 3, but I'm going to change my rate to a larger rate. Now times 10. Let's make our table of values. So our 0 value is still 3 because we're not changing that. But what am I going to multiply by? 10. So I'm going to take the 3 and multiply times 10. So 3 times 10 is 30. I'll do my next one. We have 30. Multiply times 10. What do I get?
300.
300. Woo, that's going up fast. All right, what about the third one? Times 10 again. 3,000. This reminds me of that one. Remember we talked about which one you would rather start with 3 trees and multiply by 10 each time? So it's growing rapidly. So let's graph it. So 0, 3, same value. 130. So this would be 20. This one's 30. So 130. And then we have 300. If this is 75, 300, we can't even get it on here, can we? But we know it's going to go really, really fast, like that. So make sure you make it look fast. If I try to make it look straight, it's going to go right here. And we know at 2, it's going to be at 300. So it's way up here. So on the last one, I wrote smaller rate. So what am I going to write on this one? What is it? Greater rate or larger rate? But we have the same start. And is it a stretch or compression? Stretch, yep. It is stretched out. Let's write our new function rule. How do we write the function rule?
3 times 10 to the 5.
Yep, 3 is your start times 10 raised to the x power. Good job. Seems like y'all are getting the hang of it. So I'm going to change it up, of course. You know how that goes. Let's look at the next one. We still have the same. We're going to, this time, start at 8. I'm going to do next equals now times 1/2. How do you think that's going to change it? Think it's going to be a decrease, a compression, decrease? Okay. So let's figure out the table. So we start with 8. Then we take what we have now, the 8, and then multiply times 1/2. 8 times half, what does that equal? 4. Let's do the next one. We're going to take 4, and then we're going to multiply times half. What do we get? 2. The next one? 1. So somebody's prediction was right. What was that prediction? A decrease, right? So let's graph it. We have 0, 8, 1, 4, 2, 2, 3, 1. Looks almost linear. What if I want to go to the other side of this? What if I want to find what -1 is? I'm going to put -1 up here. If I'm getting the y is getting smaller, and I want to go the opposite way to find -1, what would I do in order to find what that 1 before it was? Multiply by 2. So what would that be? Huh? So we're going from 0, 8, and then we're going up to the previous one. What would the previous one be? 16. Okay, let's go to the next previous. What would that be? What? 32. Okay. What about the next previous?
64.
Right. I've seen these numbers before. Do y'all remember what these numbers come from? Sweet 16, Elite 8, Final 4, Championship game. What was this from? The video, which was about what? What scenario? What real world application?
Tournament.
The tournament. Yep. March Madness. A basketball tournament where teams are getting eliminated. So let's go to, let's see, -1, 16. So if this is 20, 16 would be maybe around there. And then -2 would be at 32. Okay, now it's starting to look exponential. Let's go ahead and go over to -3. So 40, 50, 60. So 64, maybe around there. Yeah, that looks more of the exponential. Because down here it almost looks linear, even though we know it's not. Okay, we changed both of them, right? So it was half. So what can I say about the rate? Smaller, but this one was smaller, right? But it still increased. So how do we make it where it's decreasing? What kind of number is that?
Fraction.
A fraction. So a number that is smaller than 1. So I'm going to put down here fraction rate, or fractional rate is, what I should put. Fractional rate smaller than 1. And then the other thing was the start value was changed, so it was a higher start. And we know that it was a decrease, right? I'm just going to put decreasing is what it is. So let's answer these 3 questions. Which changes resulted in a change in the steepness of the graph? The what? What'd you say?
They said this one.
The slope, okay. Slope is specifically with linear though. So what could I say that means slope, but it could also be used in exponential? Right. Right was changed. And that's the number with the exponent in our function. Oh, we forgot to do this function rule. Let's write this function rule now. F of x equals, what do we put first in our function rule? Start, which is 8. And then what do we put next? 1/2. Where do we put the x at? Yep, with the exponent. 1/2 to the x power. So rate was changed. If the rate is changed, that is the number with our exponent. Just like with slope, it's the number with the x value. What changes resulted in change of the starting point in the graph? Y-intercept. Which is also called what in our recursive rule? Yeah, start value. How does exponential growth compare to linear growth? What could we say as a comparison of exponential versus linear?
Linear is a straight line and exponential is a curved line.
Yep. So linear, straight line. It increases by the same amount every time, right? By adding or subtracting? Increase/decrease by adding or subtracting. So it goes exactly at the same rate. But what about exponential? Okay, we said curved line on linear. So what would we put on exponential? I mean, straight line on linear. What would we say about exponential? There we go. Curved line. And what about the increase or decrease? How is it? By a lot, but what operation? Multiplying, right. Increase/decrease by multiplying. You'll take pictures, put this in your journal, and also glue it in your journal. Take pictures, put it in your digital notebook, glue it in your journal. This is your assignment. I'm going to pass this out. On the back, you're going to skip any of the division because we have not learned that yet. So you'll skip, and we're going to do that next week. So 7, 8, 9, 10, 12, 5, and 6. So really, you only need to do, oh, no, not that one. Sorry. This one. Not 7. So 1, 2, 3, 4, and 11. Those are the only ones on the back. So you'll go ahead and get started on that.